Hey, I'm Paul. I'm going to show a series of demos illustrating some of the things you can build with Unison Cloud. What is Unison Cloud? It is a distributed computing platform. It sits on top of AWS or is portable to other providers. It's something that you could run on your company's own infrastructure, or we could operate a private instance for you. And we also have a public cloud with a free tier that you can use for experimentation or personal projects. It runs distributed programs that are written in the Unison language. And you can sort of think of it as like a very fancy distributed runtime for Unison. So it almost lets you treat the cloud as if it is a single computer, a distributed computer. So you write one program, you run it, and distributed computation happens in the cloud. And then one really nice thing about it is that different distributed systems that you might want to build are expressed with nice little open source libraries that can all talk to each other and compose nicely. Here's kind of how it works. There's sort of a core technical idea that we make use of. So the Unison language supports dynamic deployment or moving computations between nodes at runtime. So suppose we have two nodes, Alice and Bob, and Alice wants to send the computation factorial of 6 over to Bob to ask Bob to compute that. There's this question of like, well, how do we send that computation at runtime? And a couple things that don't work are to just send the name factorial. That's no good because Bob may have a different meaning assigned to that name or a different library version in his environment. Another thing that doesn't work or isn't ideal is to somehow set up all the nodes in advance with the exact same versions of all dependencies. That's kind of no good. We want to avoid that. We just want to be able to write code, run it, and then it runs distributed on the cloud computer. And so instead, what Unison does is we give each definition a hash. So factorial is going to have a hash. That hash will be based on the hashes of its dependencies, product and range, and of course on the implementation of factorial itself, such that if we change anything at all about factorial or any of its dependencies, that hash will change. And so that hash uniquely and unambiguously identifies an exact version of the factorial function. And by the way, in practice, these hashes are 512-bit SHA-3 hashes. We don't need to worry about collisions in the lifetime of our universe. But anyway, this gives us a really simple, robust protocol for moving computations around at runtime. So Alice can just say to Bob, hey, can you compute this thing? Bob can inspect basically the bytecode tree that he receives, which is going to have hashes in it instead of names. He's going to check his local code cache. Does he already have the code for all those hashes? If yes, he's good to go. If no, he says, hey, Alice, I'm missing the code for this hash. Can you send it? Alice can send it on the fly, and it'll be cached for next time. So that's the gist of it. It's kind of a simple core idea, but building an entire distributed computing platform based around that idea was tricky. But we've done it, and I'm going to be showing you some demos of that. So the first demo is just going to be showing kind of some of the basics of distributed computation with Unison Cloud and some core concepts. So here's the basics of the programming model that you get to work with. So there are 3 operations: fork at, await, and pool. Okay, so fork at basically lets you start a computation in parallel on a different node, different location. So it starts that computation running in the background. That returns like a future or a promise. You can block the current thread, wait for that to complete. And you might be asking like, okay, where do I obtain a location that I can fork to? And one way is you can just ask Unison Cloud, could you give me a random available location from the pool? There's other ways as well. You actually have a lot of control. You can even do things like, oh, I want to fork this task at the same location as this other task because I know they're going to be communicating, things like that. And then the thing I'm going to show in this first demo is that just by using combinations of these 3 functions, you can introduce new distributed computing patterns. So here is a distributed parallel mapping over a list, and you write this kind of thing with a few lines of code. Cool. So you might ask, what is a location? A location is a place where computation can happen. It's sort of an abstract concept. It's typed based on what you can do at that location. So not all locations are the same. You might have one location where you can do HTTP stuff and access storage, another location where you can, like, I don't know, run CUDA code. And a location could represent either a single container or it could represent a whole pool of nodes, an entire region. And the design of this API is meant to support global distributed computation. So globe spanning distributed computations that do, one sub-computation, in US East, another in US West. Maybe you're even making these decisions dynamically. It's all designed to support that sort of thing. All right, so let's see a demo of just some of the basics here. So I have this first example. This is, here's that power map function I showed in the slides. So cool, you can define these new kinds of distributed computations, these nice reusable functions, but how do you actually submit it to the cloud? And you do that by calling a function, cloud.main. You give it a block of code that can do cloud stuff. And what can you do in this block of code? Well, one of the things you can do is submit a batch job. So that's what we're doing here. So we're calling submit. We're using the default environment. The environment, by the way, controls like what databases and secrets that batch job or service has access to. So we'll see that in a few places. Here, we're just doing something very simple. We're just in parallel distributed incrementing all the elements of this list, okay? So when I hit run here, what is going to happen is Unison is going to take this code that's passed to submit. It's going to serialize it, send it to Unison Cloud. It's going to sync any missing dependencies. Then once it has all the dependencies, it's going to run the computation distributed on this managed pool of nodes, and then it's going to send back a result. And generally this takes maybe a second or two, a couple seconds. So most of the time is actually just spent on that networking and code syncing that we have to do. But it's very, very fast. So you can submit these kind of ad hoc batch jobs, almost as if the cloud were an extension of your laptop. Cool. All right, so moving on. So the next demo I'm going to show is deploying services and doing inter-service communication. So the key idea here is that services are typed, okay? So we're going to be able to deploy a service with a single function call. It's going to take seconds. The reference to that service is going to be typed. All the call sites of that service are going to be type checked. And we're going to be able to make service calls with a single line of code. So here is an example, deploying the service with a function call. It's an album service. It's going to map a song to a list of albums that the song appears on. You can see the reference to that service is typed. You can see I'm going to call it with a single line of code. So it's sort of nice, ergonomic. We actually do something interesting to speed up service calls, something that we call adaptive service graph compression. So let me explain what that means. So traditionally, when you make a service call, you are crossing a network boundary, right? So you have the caller, the callee, they're running in two different containers. The caller has to take the argument, encode that to, say, JSON, send that over the network. The callee's got to decode that, run the service logic, encode the result, send that back over the network, and so forth. So there's a fair amount of network and CPU overhead to just make the service call happen. Unison Cloud service calls work differently. So because we can move computations around on the fly, we can do something really interesting. So we can move the code of a service to the call sites, the places where that service is called. So when you go to call a service, we actually just check, is that service code already available locally? If it is, great, we make what is essentially a local in-memory function call to that service, and it's super fast. If no, that's fine. We grab the code for the service from storage and cache it for next time. And so what this means is that the service graph is no longer static. So it's not like a fixed topology where services are running in particular containers. Instead, it's like services that are talking to each other are being dynamically co-located to exist in basically the same container, eliminating a lot of that network overhead and latency and compute cost that comes. It's actually this capability of being able to move computations around it's not just for speeding up service calls. Almost any kind of distributed system benefits from being able to do this sort of dynamic code moves to data optimization. But this is just one kind of cool example of how we make use of it in Unison Cloud. Okay, let's see a demo of this. I'm actually going to show two examples. One is just deploying a regular old HTTP service. So you can do that too. That's very common if you're going to be deploying something that talks to the outside world or the rest of your system, needs to speak some HTTP protocol. That's fine. So here is a simple hello world service. I run hello.deploy, and it takes a few seconds. It's made live, running in the cloud, and prints out the URLs for accessing it. Let's just jump over here, and we can say like, hi, testing. By the way, I'm running this on staging. That's why the cert issue. But anyway, if you're running this on prod, you would not see that. Also, you can deploy both to a custom domain or to default URLs here. So you can say like hello Alice, hello Bob, and this is just sort of echoing that path parameter. If we want to view the logs for the service, we can jump over to here. This is app.unison.cloud, and open up the logs, and we should see some stuff here. You can also stream logs to your local console if you like. So yeah, that's deploying just regular HTTP-based services. Okay, so the next thing I'm going to show is actually deploying a collection of services. So I'm going to be deploying both a backend service, which is going to be a native service that actually is even accessing a database for looking up some information, and then there's going to be an HTTP-based edge service that makes a call into that backend service. I won't go through this code in detail, but maybe a takeaway here is that you just write regular Unison code to deploy multiple services and wire them up together, and it's no big deal. I'm actually even doing a little batch job here to populate data that's used by that service. And I guess the main thing here is here's the actual remote service call to that backend service. A nice thing is that, as I mentioned, this is type checked. So if I try to pass some stuff in here that is not what the service is expecting, I actually get a type error before even running anything. So it's a nice experience. Okay, so if I go ahead and run, this is music app.deploy. It's going to be doing a couple things. It's deploying these two different services. It's running a batch job to populate some data that's used by the backend service, and printing out the URLs. And yeah, it takes a few seconds. Generally, anytime you want to do something, get the cloud to do a thing, it's a few seconds. You're not like waiting 30 minutes or something for CI to build a multi-gigabyte container and ship that somewhere. Okay, let's go ahead and hit this service. So here's that service. I can look up songs. So here it looked up "Cruel Summer." Appears on the album "Lover" by Taylor Swift. My daughter is a huge fan of Taylor Swift, by the way. Okay, and then also what was the other one? Shadow Journal. That was the other. And Shadow Journal appears on the Blue Notebooks by Max Richter, which is a great album. Cool. So that's deploying multiple microservices, getting them to talk to each other, wiring them up, and it is super nice, and it's a very convenient ergonomic experience. Okay. Last demo that I'm going to show is distributed stream processing. So kind of the big idea here is that just using combinations of the primitives that I've shown so far, you can build these big, interesting distributed systems with absolutely tiny libraries. So this library that I'm going to be showing, it's about 2,000 to 3,000 lines of code, depending on what you count. Just sort of for comparison, something like Kafka plus Kafka Streams is over 1.2 million lines of code. Not an entirely fair comparison. So that's a great technology. It's been around for a while and can do a lot of things, but just trying to give you a sense of, you can build really interesting stuff with very little code. Here is the example I'm going to show. I'm going to show a streaming distributed word count example. So, and it's going to be using this distributed streaming MapReduce implementation, which is 4 lines. I won't go through this code in too much detail, but it's kind of working in 2 stages. It's reducing all the keys in parallel, and then it's combining, sending all the keys to one stream and reducing that stream. You can also do like a multi-stage distributed reduce, but it just kind of kept this really simple. Okay, so let's run this example. So first thing I'm going to point out is that you can take any distributed thing that you define with Unison, and you can run it locally too. So you don't need to run it in the real cloud. You can just run it on your local machines with sort of simulated distributed execution. You might even do that with like simulated faults injected, things like that. So that's what this is what I'm doing here. I'm going to just run streaming MapReduce. And here's the pipeline, data pipelines being deployed. It's calling that MapReduce function, doing word count. And yeah, and then it's posting a few events to the input. So I'm going to go ahead and run this. I added a little bit of a pause so you can see what's going on at the end before it shuts down. But you can see the events coming in and the count being updated after each event arrives. Okay, so now I am going to take that same data pipeline and deploy it to the cloud. And so if I go ahead and run demo.deploy, so you can see it's the same data pipeline here. It's this streaming MapReduce of word count, and I'm going to run demo.deploy. In hopefully a few seconds, it is deployed to the cloud and running. But like, what does that mean? Well, it's there. It's the data pipeline it's sitting there. It's waiting for events to be posted. So there's a few ways that you might publish events to one of these pipelines. More typically, you would probably just write a service, either a WebSocket or HTTP-based service that would let you ingest events, massively parallel distributed, feed that to the pipeline. Here, I'm going to just run a little batch job that submits the events sort of manually to the pipeline. So I'm just literally calling cloud.submit, kind of the same function we used earlier. And I'm going to publish a few of those events. But actually, before we do that, let me just hop over. This is how we're going to see the output messages. So you can see nothing's been logged yet on that service. But if I go ahead and run demo.publish, it's going to submit this little batch job to the cloud to publish those events. And if I go ahead and refresh the page, we can see the events coming in, being ingested, and those counts being updated. Okay. Cool. So that is it for the demos. But we have a number of other use cases that we've worked on. It is often shocking how little code you need to express different kinds of systems. It is super fun. It's honestly, most of the time that you spend building a system it's not writing the code. It's actually just like thinking and understanding, well, what even is it that I want to implement? And once you're clear on that, it's often, not much work at all to build the thing. I want to sort of just take a step back and look a little bit at the future, something that we're calling compositional distributed computing. So when you're writing code that runs on one machine, it's this very nice compositional experience where you can just download libraries and make function calls into those libraries. At the level of distributed systems, we don't really have that. We have these big frameworks and products which are kind of siloed off from each other and which are often sort of held together or stitched together with duct tape and baling wire. But on Unison Cloud, all things distributed, anything that you build or that anyone else builds, it really can be a library, and you literally can download that library and make function calls into it. And you have a common type system, and everything sort of snaps together. And it's something that I think can be a very nice, much more uniform experience when you're composing these bigger distributed systems. So thanks so much. I hope you like this demo.